This is the Amp Hour Podcast. Released September 3rd, 2019. Episode 456.3. Discussing Fomu with Tim Ansell and Sean Cross. Welcome to the Amp Hour. I'm Chris Gamble of Contextual Electronics.
I'm Sean Cross from Kosagi Electronics.
Hi, I'm Tim Ansell from a lot of different projects.
And I'm Michael Ossman from Great Scott Gadgets.
Hey guys, we're in a field in Germany. Why aren't you guys speaking German? I was
don't
thinking
know.
the first interview I do is with people that are from the U.S., but hard to pin down. So I thought this is good. You know, we don't have much going on. The sun's setting on the last day of CC camp. It's a good time to go. So, good talking to you.
Mein Deutsch ist nix so gut.
I don't know any German whatsoever. I barely speak English, let alone another language.
So, Mike and Tim have both been on the show before. Sean, why don't you tell us a little bit about yourself?
Well, I live in Singapore, which is far away from many things, but it's close relatively to China, which is very nice because it means that I can visit China relatively often and actually do factory production. So lately I've gotten into doing a lot of hardware projects. In particular, the Fomu is the FPGA in your USB port that we've been working on. So being able to travel to China to do factory management, but come home to Singapore is a really nice property of being able to live there. Mm-hmm. So in addition to doing the factory design, I've been working on the PCB and the software and the firmware. So the point with Fomu, and correct me if I'm wrong, Tim, is to trick software people into becoming hardware people. And Tim has done a fantastic job tricking me into becoming somebody who is now an FPGA developer, doing low-level FPGA development on things such as the USB stack.
Yep. So Sean also did the original crowdfunding and productionization of the Fomu project, which is a little ARM microcontroller that goes in your USB port. He didn't learn the first time, and so he's now doing it for the Fomu. And we came to the camp to give a talk on this process of taking a device that is an idea of mine, and then Sean being stuck with actually turning it into something that people can get, which is pretty interesting because I have a lot of ideas, and making them reality is a lot harder than necessarily having them. And so it's been really great working with Sean on this project.
Yeah. And Sean, we also know you from the laptop you worked on.
Yeah, so one of the things we did is the previous company that brought us to Singapore, that company ended up, it was a startup that was a little bit past its prime. So it went under and they offered to pull us all back to the US. But both Bunny and myself decided that we wanted to stay in Singapore and just do our own thing. And up until that point, we had been doing somebody else's projects or some CEO or whatever the company wanted. But we realized that we both wanted to build our own laptop from scratch. People build their own desktop by taking parts together. Well, we thought, let's take it one step further and do a laptop that is completely weird, has all sorts of bizarre features that we find interesting that you might not find in a normal laptop. Features such as an FPGA, which we used for a couple of other projects, such as doing SPI emulation for reverse engineering SD cards, or reverse engineering how a particular MediaTek chip worked for mobile phones. So having that all in our laptop meant fewer pieces of hardware that we had to take around with us when we visited various conferences.
So I like to describe Sean as being Bunny's software guy and my hardware guy, because he's silly enough to do all the hardware productionization for my projects. Still ends up doing a lot of the software as well, because I don't have a lot of time with my many projects that I'm involved with. But
Tim,
yeah.
I've never heard this about you. You're saying I have many projects.
Yep.
Too many projects, in
Yes,
fact.
I even give a talk about that.
Yes.
So, yeah, normally it's a 5-minute talk, but I think the last time I tried to give it, it ended up being 20 minutes. So
Nice.
it's gotten very long.
Yeah. So let's talk about the hardware stuff. So, I mean, is there a fundamental, and Mike, obviously you do a lot of hardware too. You know, is there a fundamental difference about putting an FPGA on a board, especially because you have the experience doing the Tomu and now the Fomu? So, yeah, order.
Okay.
Yeah. Is there fundamental differences about working in FPGAs and putting stuff on boards like that, or
Do you mean from a hardware perspective, from designing the boards, or do you mean from a user perspective as somebody who actually wants to use the thing on the boards?
No, I meant on the hardware perspective. So, you know, like as you're pushing through design decisions, you know, doing layout, stuff like that.
Well, doing layout of FPGAs is much more difficult because with a CPU, you have things like this is what the maximum current draw of this will be, and these are the voltage rails that it will have. But when you're designing an FPGA, almost by definition, you don't know what it will be running, so you don't know what the maximum current draw could be. I mean, you can always come up with some pathological bit stream that toggles everything on and off at the highest possible rate,
Right.
and now it'll suddenly draw a whole bunch of current, which means you'll need to put more power down than for something that is just sitting idle most of the time.
Right. So higher cost then. Or,
Higher cost, you need beefier regulators.
Yeah.
In addition, FPGAs tend to have more power rails, and so they tend to be a little bit more finicky when it comes to power sequencing. One of the things I've noticed is that a lot of designs for the ICE40 that other people do don't tend to do power sequencing according to the specs that Lattice gives, and it turns out that that is fine. The ICE40 is a pretty forgiving chip, but I know, for example, with some of the Xilinx parts that Bunny has used, he has swapped the power sequencing a few times and destroyed a few chips that way. So FPGAs are particularly finicky when it comes to just power sequencing, you know, which power line gets turned on first.
Yeah. And for listeners, can you define what that means?
Sure. When you have, for example, USB is 5 volts, but when you have a chip such as an FPGA or a CPU, you're going to have different voltage levels within the chip. So for example, on the ICE40 that we use in Fomu, the logic all runs at 1.2 volts. And all of the input-output pins, we have defined that they run at 3.3 volts. And then there's also a on-chip ROM that requires 2.5 volts. And so there are 3 different voltage levels that you need to feed this thing, in addition to the fact that Fomu is a USB device, and so it takes 5 volts in. So you need to have various regulators that will then go from 5 volts down to 1.2, down to 3.3, down to 2.5. And with other parts, such as Xilinx, you have 0.7.
Sure. But do you mean they have to like track together and like come up at the right time? And...
It might. So with the ICE40, the 1.2 has to come up first. So you have to attach the 1.2 volt line to the CPU before you can pull up the 3.3 volt line. So if you get that wrong, it may be that one part of the chip is powered before the other, and that could cause things like voltage to flow in a direction that it might not need to go to. So the chip might get warm, it might think that you're shorting something out. The ESD networks that prevent it from dying when you touch it after walking across a carpet, they tend to be very finicky when it comes to this sort of thing, and that's why sequencing power is very important.
Okay, that makes sense. Yeah. Yeah. So okay, so that's like the layout side of things. What about as you're moving into firmware and developing things there? I mean, are you starting from scratch? Are you starting from some of the existing Ice Storm setup? Is Tim doing anything? That's the real question.
Well, Tim is helping with getting some of the tools set up. So for example, the ICE40 has this MAC block that lets you do advanced multiplication, for example. Normally when you put a CPU multiplier in, it takes about 500 gates, for example, which when this CPU has 5,000, that's 10% of your CPU that just goes to a multiply unit. The ICE40 has special DSP blocks that you can use as multipliers, but they require you to either come up with a multiplier yourself or use a thing called inference, where the software that actually generates the bitstream file can infer these multiply blocks and figure out how to combine them based on what the code you write. And this is a thing that we're trying to get into the synthesizers that we're using on ICE 40, in particular Yosis. And I know Tim has been helping to try and get that into those tools.
Yeah, again, though, I'm not actually doing the work. I tend to do more of the management side of things, finding funding. One of the big parts I played in the Fomu project was we did this Fomu hacker board, which basically violates all the good rules of doing hardware to make it quicker and easier to produce, so that I could give out boards for free. And one of the things we've been doing here at camp is running workshops using those boards, and that's helped build a community of people who have more experience with these parts and are able to produce examples and demos. Again, the kind of idea here is that I don't do the work, I don't have to write the demos. Everybody who kind of gets hardware kind of has a chance of developing something cool and interesting, and that's kind of the deal. Is like, I will send people hardware or give people hardware in the hope that they do something cool and interesting with. And so I spend a lot of time helping people get over that hump and, you know, trying to find funding to do these type of things and that type of thing. So I've somehow become a manager for my hobbies, which is less fun than I'd hoped, but it's really cool to see like things come to fruition, like seeing the production Fomu, which is like better in every way than the hacker thing. It has things like ESD protection, which the hacker version doesn't have. Is like really awesome. You kind of look at them side by side and you see like Sean's one is like really nice, neatly laid out, and the hacker one is kind of like pushing the limits of what you can do, and so that's really cool. And I've been trying to find people to work on like the USB stuff, and trying to get people to collaborate as well. One thing I'm actually quite excited about is related to Great Scott's Gadgets, which is this Kate is working on this USB stuff. Our USB stack that we use on the ICE 40 is written in a HDL language called Megen, which is also Python. And so the fact that this USB stuff is Python, we think there's a whole bunch of interesting things when you combine these two pieces of software together. And so Zobs has been worried about like making the USB stack really work, while I've been trying to add new features and better ways to test it and all this type of stuff. So,
Mike, can you tell us about the USB stuff a little bit?
Sure. And so we have a number of different things going on USB-wise at Great Scott Gadgets, and Tim just mentioned Kate, who is our lead software developer and also does a lot of hardware and other things at Great Scott. At Great Scott Gadgets, and
I will mention too, Kate and Michaela were just on Alvaro's Reverse Engineering podcast too.
Yes,
that was good.
They were. Alvaro visited us at the lab, and I waved at him and had to go out the door, and so I was glad I got to spend some time with him here at camp, because when he was in my town, I saw him for 2 seconds. But that's a good podcast where Alvaro covered a bunch of the bases of stuff that Kate and Michaela had presented at Teardown, and basically what Kate and Michaela have been working on lately is a variety of USB tools for USB analysis, USB hacking, USB troubleshooting, USB development, And some of that is based on our GradeFet platform, which is in large part a USB hacking platform, and but part of it is also based on other tools, including hardware tools that are as simple as a $5 logic analyzer and doing USB analysis with that kind of thing. But also on the other end of the spectrum, using FPGA-based tools, things that are much more sophisticated, and that kind of goes back to an old project we had at Great Scott Gadgets called Daisho that I've actually talked about on old episodes of the Amp Hour in the past, and that project never became a commercial product, but it allowed us to develop a bunch of interesting things like an open source USB core for super speed USB on an FPGA, and that's something that has kind of lived on since then, and we're hoping continues to live on and lets us do some exciting things in the future.
Yeah, so as someone who's firmware silly, stupid, me, what is the hard part about USB? I mean, I know it's hard. I just know it's hard because a lot of the stuff in firmware field feels hard to me. But the three of you were just talking about USB and the struggles that it's causing, and obviously the tools that you're working on. So, like, what is the hard part that has to be solved still?
There's many things that need to be solved still.
Because the reason I say this as a comparison is like, we're talking on a device right now that has USB stack on it. I realize that it's a USB mini and it's slow and it's whatever, right? But like, everything has USB, and so obviously this is a replicated problem. Lots of people are having the same problem. So is it just that it hasn't been solved in a replicable, like, open source way?
So there are plenty of good USB stacks available. Tiny USB, for example, is a very common one that is very simple to implement and has a lot of features that you can use.
That's the software-based one?
Software-based. Well, no,
Yeah.
so Tiny USB is a USB stack that you would use, for example, with an STM32
Oh, okay.
or anything that has a hardware USB block in it.
Oh, okay. Because there was one, MG was just in the show, and he talked about putting on the AT Tiny, and I didn't know what that was. Maybe it's not that
Yeah,
one.
so there was a software one for the AT Tiny called VUSB.
Okay,
That's what he's using.
Yeah, okay.
And I did one for ARM microcontrollers that's called Granuum. And so that does bit banging USB full low speed on a 48 megahertz ARM micro.
Oh, nice. So you get it kind of for free, right?
For free, yeah. And this is a microcontroller you can get for under $1.
Yeah.
That is a full 32-bit ARM microcontroller. So there are two different things here. There's the PHY layer and the MAC layer that we're working on, which is things like if you were to hook up an oscilloscope or a voltmeter to a USB cable, what would the actual signals look like? And then on top of that, as you go up, you get things like how are the frames grouped together? How are the packets grouped together? Which transactions come before which? You have token packets, you have data packets, and you have acknowledgement packets. Getting those in the correct order and making sure that all the checksums match and make sure that you reject packets that aren't good, that is something that a lot of times is handled by the hardware.
There's like a set of shift registers or something that's happening internally?
Right, so they're taking care of the CRC16.
Got it.
They're taking care of when the host requests data from the device, they'll automatically create the in packet, put the data in there, add the CRC, and then send the acknowledgement. So the hardware will take care of that. When you're doing your own USB stack, you have to worry about all of that.
Got it. And so if you're doing it software specifically, then you're doing it in a serial manner. You're saying, wait on this line, sit there, wait for this data, get the CRC calculated, and all those things?
Right, and so that is different for each bit of hardware. And so when we do this on Fomu, we need to come up with something that works with the correct clock domain, does the correct sequencing. There's all these aspects that we have to get right, otherwise it just doesn't work. And one of the places where these tools come in handy is a lot of times when it doesn't work, you plug it in and it just says doesn't work. There's no why doesn't it work.
Right.
So having a logic analyzer such as the Great FET can be very handy in figuring out, oh, it's not working because, for example, my string descriptor is incorrectly formatted, or I'm not listening to the set address command and I'm sending the wrong address. All these things where if you're just using a consumer desktop PC and you don't have this fancy hardware, it's very opaque and you have no idea what's going on.
Okay.
And so a lot of the USB analyzers cost significant amounts of money. There's a very popular one called the Beagle, and I think that kind of starts at the $200 to $500 range, and like if you go to the more advanced ones, they start to get to the $5,000 range. And as well, there's no good open source compliant test suite.
So it's not just about the hard. Like, I mean, $5,000 is a lot of money, but it's not just about the money, right? It's about the system.
I think, like, it is somewhat about the money because it means that there's just not enough people banging on the problem. There's this kind of high barrier to entry, which means that if you're trying to do something a little bit different that is not on the standard, like what everybody is doing, like what we're doing with the Fomu, where we're like doing our own custom USB stack in the FPGA hardware, things get a lot harder. If you go off the beaten track, there, because of the cost, there's a lot less beaten track.
Right.
And as well, not all this hardware is particularly like good in telling you like whether you're doing something correctly, but it's a little bit different versus doing something that is actually wrong. And USB stacks on computers are fairly forgiving in many ways because there's lots of really bad hardware out there, which kind of is self-reinforcing in that then people can write, you know, partially working USB stacks that work just well enough to get things working. If you go and look at, for example, the USB serial driver in Linux, the number of like hacks for workarounds in to get various hardware working is like enormous. And so Zobs was talking about all these pieces of hardware having hardware USB stacks. Frequently they're not actually very good either.
Okay. They're just more permanent.
Yes, you can't change them. And I think that's one really interesting thing about the FPGA is like we've been coming across these problems at these workshops, and Sean has been able to like look at them and start fixing the problems, and then everybody can get the fix.
That's right.
And that's how I actually got into FPGAs, was thinking about a similar idea with displays on
Someone's DECT phone's going off.
Sorry, that's my DECT phone.
Mike, you have to explain what a DECT phone is now. Sorry.
yeah.
Well, sorry to interrupt him, but here at camp we have an entire infrastructure all over camp where you can use mobile phones, including GSM phones, but also including DECT phones, DECT, which is the very popular standard for like home cordless phones.
Like 900 megahertz.
Well, like what
E
used to be 900 megahertz in the U.S.
Yeah.
Now in the U.S., DECT phones are very popular. They run on a slightly different frequency than the DECT phones here in Europe, but they're basically the same otherwise. and we have you have the ability here at camp just to bring an off-the-shelf German decked phone and just carry it around camp and be able to talk to anyone else on the phone network, which is pretty cool. And so I have this this rather crude decked phone that I forgot to turn the ringer off of. And honestly, I don't know how to turn the ringer off on it.
I had to power my whole thing down.
I'm just gonna take the battery out.
It's kind of cool that a lot of this stuff comes from software-defined radio and a lot of the GSM infrastructure.
Yeah, Osmocom's running like all the towers and stuff. Towers, which aren't on towers, they're just on a desk.
So there's a lot of FPGAs in them. Again, because they can continue to improve it after the fact. It makes your hardware into software. And I think that's a really cool thing about FPGAs and why I'm excited about FPGAs. And I was kind of saying before the phone rang is that I got into them because I was frustrated with this experience when presenters got up to the front of the conference and plugged in their laptop and then spent 10 minutes trying to figure out how to get the stuff on the screen, and there was like nothing you could do about this. And with an FPGA-based implementation of the video system, we could continue to evolve, and every time we ran into a problem that prevented a laptop from working, we could improve the software, and we could improve the hardware because of the FPGA.
Right. It wasn't some chipset that you're just like, oh, well, it's stuck on the board. Got to deal with it.
Yep.
Borrow someone's laptop that works, right?
Yep.
And that's actually what we use for KaiCon, too. So.
Yep.
It works. Verified working.
So we'll give your listeners a tip when it comes to getting USB validated. As Tim mentioned, Linux is incredibly forgiving when it comes to descriptors in your USB device and things like that. If you have access to a Windows machine, Windows is very much not forgiving. So if you have things like invalid USB indices in your descriptor, or if it's the wrong length, or if sizes don't match, Linux will do its best and just continue on, and your device will work. Windows will tell you it's broken.
I've gotten that message many times, yeah.
So if you want to validate your machine, your USB configuration in your product, whatever it is, works, plug it into a Windows machine and see if it enumerates at all. See if it pops up with an error saying there's something wrong. Again, just like with everything else, it won't tell you what's wrong, but it will tell you that something is wrong. So that's a very good first approximation of whether or not your thing is working or not.
And so I just use Linux. I haven't used Windows pretty much
many years
since 2005-ish. And so I was working on some of the very early initial USB stuff. So I'm pretty sure what I gave Sean that was like in a barely working state in Linux probably was totally broken on Windows, which Sean does use. So he had to fix a lot of those type of problems. But I do think it would be really nice to have a fully open source compliance suite that we could use to test a lot of this stuff and like test it in simulation so that you don't have to have the hardware to check whether or not it works. And that is another one of my many projects that I'm trying to find people to work on and get funding to do is build a better compliance suite for USB so that as people develop these type of things, it becomes easier to make a fully working compliant USB suite. And a lot of the stuff that Sean is working on, and I'm hoping a lot of stuff that Kate's working on, will kind of, in many ways, merge at some point, because there's no point having a compliance suite if it doesn't tell you how things are wrong, and like the protocol decoders are really important and be able to like understand why this isn't working and give you useful information about what you're doing wrong.
Right.
Yeah.
And like back when we were working on the Daisho project, we were implementing this super speed USB core, and no one had ever done that before in open source. And so And also, super speed USB was pretty new at the time. And how did we test our core? Well, there was no real way to do it other than buying a super speed USB analyzer that had compliance testing capability, and that was tens of thousands of dollars just for one piece of equipment to do that.
Like, I'm pretty sure if you have a high-end oscilloscope, just the software for compliance testing is in the order of 10 or 20K USD. Wow. It's very expensive to get USB compliance testing stuff, and that makes it very hard for people who are doing open source projects to actually check their implementation is compliant.
Right, and because it matters because you're going across so many devices, and like everybody uses USB. It's just everywhere. So.
Yep, and there's lots. The other thing compliance doesn't really help with is there's lots of bad implementations out there, and there's lots of stuff that doesn't quite work properly, and so it's not good enough just to test compliance. It's also you want to test for known bad situations, which is something the compliance suites have never done, but we would be able to do in open source versions of these suites. We could have we know this piece of hardware is broken in this way, here's an emulation of that, which would be really cool. And so
that's great. So I want to shift a little bit because selfishly I was unable to explain why all this open stuff matters. We're kind of talking about the openness here, and I think Mike's always done a good job talking about openness and why it matters and stuff too. But so Dave kind of approached me and he was like, so why are you actually excited about all this open FPGA stuff? And I'm like, I don't know, I just kind of am. It's hard to say why. I think there's some high level things, but from the three of yours perspective, why is all this stuff, why are you working on it in the first place? Why does this matter? Why is this important? Specifically for FPGAs, because it's not just open tools, it's open tools for FPGAs.
Well, there's a lot of cool things you could do with open and FPGAs. I'm going to talk about the open part first. We, as Tim mentioned earlier, we gave several workshops here at CC Camp, where if you came and you installed the toolchain, Tim would give you a Fomu unit, a Fomu hacker unit, and then you could then proceed to take the workshop and then do the self-directed workshop yourself. The process to install the toolchain was to extract it onto your system in set path. This is a complete departure from, for example, the Xilinx toolchain or some of the other toolchains where you had to first download a 15 gigabyte file, then you had to register it, and then you had to get a license, which usually ended up either coming up with a serial number for your system or figuring out what the MAC address was. It varies from system to system. Then you have to install it, which can take a lot of time, and then you had to run it. And there are so many barriers to entry just to get that large toolchain installed that it was a big turnoff for a lot of people. We had a Spartan 6 FPGA from Xilinx in the Novena laptop, but hardly anyone used it because this toolchain was just so unwieldy. So being able to have, how many people do you think came? 300, 400?
I think even more than that. I'd say 5. I think I gave out about 500 of the boards. 500
people attending this workshop, and we had, I think, 2 or 3 people who were unable to download the software and get it running. And that was mostly because we don't support 32-bit Linux at this point. So it's just a matter of recompiling the software. But making it so easy for people to get into FPGAs is a huge thing that open toolchains get us. Now, what can you do with that? One of the really cool things we have on Fomu is we have this USB wishbone bridge. So in the FPGA, and this is what makes a lot of this really cool, we have this wishbone bus. So in your computer, it has a memory space, and that's where your RAM is, that's where all of your peripherals tend to be. So there's a special area in memory of your computer where there is a copy of everything that's on the screen. So your screen has a frame buffer in RAM somewhere. And if you happen to know that area of memory and can write to it, you can manually put pixels on the screen. This is how it used to work a long time ago in the DOS days. Since we have this wishbone bridge on this device, we can peek and poke values in memory from the host PC without the CPU carrying, the CPU that's on Fomu carrying. And we can actually go one step further, and we can connect a debugger to the CPU that's running on the FPGA and do things like single step, insert breakpoints, examine memory, reset the CPU, which if you were to do that with, for example, an ARM microcontroller, you would need a separate JTAG box. You'd need a separate debug box that you'd also have to plug in. So that's more to carry around with you. It's a little bit complicated to set up, but because we have this open USB stack that we can modify, that we've created, we can provide this easy-to-use debugging experience to anybody who wants to grab it and just get going.
So, as I think I mentioned in the last time I talked with Chris about FPGA-related stuff, is that my general philosophy is to try and do as little as possible on an FPGA, because no matter how easy you make FPGA development, you're still describing hardware, and that is does take a bit of work to do.
Sure.
And so in pretty much every FPGA system that I work on, the first thing we do is get a soft CPU running on the FPGA and then write C code generally to run on that soft CPU to do all the management style tasks that happen at a slow pace and, well, slow for computers, still extremely fast for humans, which enables us...
Some examples of those.
Things like I²C or checking that you're running the right set of software on the right set of device,
So kind of tapping into existing code bases and using that kind of thing? Yeah,
on some of the bigger boards which have external DDR memory, they have to be trained when they start. Doing that training, it's much easier to write that training in C code than it is to write in FPGA code, and it's much easier to get right, and you can write like tests for it and stuff like this. And so when we're doing the Fomu, we did the same thing in embedding a little RISC-V core in the FPGA, which runs most of the higher level code, and even the bootloader tends to be mostly C code running on this RISC-V. Sean, again, when I handed it to him, there was no bootloader. He wrote a new bootloader on top of the USB stack, and that's a DFU bootloader, which DFU stands for Device Firmware Upgrade. It enables you to very easily reflash the Fomu, including using things like web browsers to flash. And one of the cool things Sean did that I hadn't even considered was that, well, we already got a RISC-V CPU there. Why don't you just DFU across a RISC-V binary? And so, I have no idea how Sean figured out that we should do that. But
can you explain what that means?
So with an FPGA, normally you load what's called a bit stream,
Sure.
which is the configuration of all the gates in this field programmable array. So when we say we have a RISC-V core on there, it's this Verilog code or this MeGen code that gets generated into a bitstream file that you then load over this DFU protocol. In the FPGA file, there is a special header you can look for, and if that file exists, then you know it's a valid FPGA file. Well, I thought, the bootloader is running on a RISC-V CPU. Why don't we let somebody upload a RISC-V program instead of a bitstream? So, because we already have the code there, instead of loading this new bitstream, just have the CPU jump to the new program that somebody has uploaded.
So that's like a firmware upload, but into an FPGA fabric?
It's not even a firmware upload. It's a software upload that you are now able to execute this RISC-V code using the CPU on there already. So it's just like you would use a normal microcontroller, for example, where you compile your C code into this binary file that you then upload. Well, we can do exactly the same thing where you compile your C code into a binary file, and at that point, you don't even treat Fomu like an FPGA, you just treat it like an embedded CPU, and you're writing RISC-V code now that you then upload to it, and it just executes as if it were a CPU.
And this is one of the things I really find delightful about the workshop, is how it exposes these kind of various layers to people who maybe potentially new to all of these layers, but you can write Python and run it in MicroPython, right? But MicroPython is running on top of this RISC-V CPU.
Right, there's an interpreter in C code written for the RISC-V, right?
Yes, so there's a project called MicroPython that is designed to embed Python on microcontrollers, all the way down to, I think, 32 kilobytes of RAM is the smallest amount they need. And it's just written in C code.
Yeah.
For now, mostly it's for ARM, but because it's C, we can just recompile it for RISC-V, and it just works natively.
Yeah.
And so on the Fomu, you can write Python and have it interpreted and in MicroPython on the device, or you can write RISC-V code, compile some C code into RISC-V instructions and have that running on the device, or you can generate a new bit stream for the FPGA and have that running on the device, and kind of all those layers are available to you all at once, which is kind of amazing to me.
Yeah.
Yes,
So I think last time I saw Sean, I was like, you have to make the real full stack developer. You're not a real full stack developer unless you're getting all the way down there, you know?
Yeah, so we don't actually we don't even call it an FPGA, really. We don't expose the reader to hardware description languages until part 3 of the workshop.
Yeah. No, I like that. And I think that, I mean, Verilog is very C-like, but it's always been kind of, you know, once you move out of like the sequential order of code, you start to be like, what's going on? You know, just telling people hardware is going to scare them away. So it's, you know, you're kind of shoehorning software people in. You're like, you're tricking them. It's great.
Yeah, Verilog is C code if every line of your program was executed at the same time.
Yeah, right.
Which is just, it's, you know, that technically it's true. You can say A equals B, B equals A, and that's how you swap the two values, because those are both executed at exactly the same instant. It can be a little bit scary to people at times. And so trying to ease them into that by first going by way of RISC-V code or Python code is kind of a nice way to give people value for this thing that they now have without needing to jump in on the deep end.
Right.
So, like, one thing I've always said with, like, FPGAs is, like, the first thing you do is you blink an LED. The second thing you do is design a CPU. There's this kind of giant gulf between, you know, the beginner workshop and the next step.
Right.
And a lot of what we're trying to do here, and this is, again, where I'm coming up with ideas and other people have to suffer with actually implementing them, is trying to make it easier to transition from having a system and moving more of it into hardware. And so the idea is, like, you can start with running MicroPython, and then the system on chip that is running in the FPGA is configurable in Python, and so you can change the peripherals in the FPGA by just changing a couple of lines of Python code, and then you get new peripherals in your FPGA. Eventually, this means that they're just going to appear in MicroPython. That is something that doesn't work yet, but is on the roadmap of things we want to do, so that, like, if you add a new SPI controller, all of a sudden your MicroPython has a new SPI controller.
So it's like generated code based around that kind of...
Yep.
Yeah.
And then maybe you decide that the peripherals you have are too limited. You can start designing your own peripherals and, you know, adding them to MicroPython. And this kind of makes it much easier to, because you can start with a simple peripheral and slowly get a more complicated peripheral. And some of this is demonstrated in the workshop by like, you can like import the machine thing and then read and write a bunch of memory locations to like control the LED system. And Sean did this pretty amazing thing where you can bridge over the USB and actually run those peek and poke commands on your computer. And so this gives you a very easy way to like understand how an existing peripheral work and how you might, you know, create your own peripheral and then peek and poke your own peripheral, which I think is really cool.
So the promise of FPGAs is you can do anything with them, right?
Yep.
Effectively. But, you know, and I like that the workshop takes people through from like software down to hardware, and in the way that you do it. But like, kind of to go back to the discussion and to help me out on when I explain it to people, like it's almost like a argument for FPGAs or like something like that. But what are you usually telling people, like why an FPGA is important in a system, right? Are you telling people that yeah, you should just go design it? So like, if you're gonna like pitch Mike on putting an FPGA into a product, is it like you're pitching it based on customization or something like that? How are you pitching an FPGA? Not that it's your job to, but just that, you know, the selling point. Again, the why does this all exist, you know?
So this is kind of the area that I tend to spend a lot of time doing in instead of doing useful work. But like it depends on the person and what is important to them. There are definitely areas where FPGAs are like essential to being able to build a product, and they tend to be areas where you need extremely high-speed I/O, or you have very high data rates.
Yep. Pipeline data through a thing, right?
Yeah, things like video processing and things like software-defined radio, where you have streams of data that you need to process simultaneously, and they tend to be very quick. And so in those cases, you're selling FPGAs just on what an FPGA is able to do. But there's a whole bunch of other areas where FPGAs make sense because they let you turn hardware into software, as we were kind of describing earlier, and so you can make product decisions at a later date. You can fix security bugs after the fact.
Yeah.
You can add new features.
Although there was that Zinc, you see the Zinc security bug?
Yes, and the interesting thing about that is most of their security problems
in the ARM
are
core?
in the non-FPGA side of stuff that they can't fix.
Right.
Whereas if it had been a soft core, they could have patched it and be on their way.
Yeah, actually that is a good comparison point then, huh?
And so, like, FPGAs do pay a price for their configurability. They tend to run slower than the equivalent ASICs, but that flexibility can be really useful in many applications. And it turns out in most cases the performance isn't particularly needed. Like a good example is in like the video control system. We need the performance for the video sequence, but for the command line GUI that lets people, you know, change which video input is connected to which video output, that is like super slow, right? It's human speed.
Yeah.
And so in that case, a CPU is more than fast enough, and even a CPU running at this type of speeds that you can implement a CPU and FPGA is like more than fast enough. And that configurable nature is really useful. It lets you make trade-offs at a later stage. Do you want to do more computation now? And do you want to be more flexible in the computation? One area that FPGAs have had a lot of success in is in machine learning, and Microsoft has been using FPGAs for machine learning because they've been able to make different trade-offs that you can't make on a CPU, like maybe a 5-bit value, which is not a value a computer is very good at dealing with,
Right.
but an FPGA doesn't care. It tends to be very good at any size thing, and so you can make different trade-offs. Maybe a 3-bit is the better value. You can match your system much closer to the data and much closer to what you actually want to do. And that's really powerful. And I think the thing that's been holding back FPGAs from being used in a lot of these applications is how hard the tooling is, the fact that there is no standard library. We were talking about USB earlier. The USB 3 core that Mike and Co did is a really useful fundamental piece of IP that you don't need to develop from scratch anymore. You can just use his core, and actually help fund some work to take his core and make it generic so you could use it on pretty much any FPGA, and now we're working to make it usable without external hardware, so you can use the high-speed transceivers in the FPGA.
Oh, nice.
And I've managed to find some funding for that, and that will enable a whole bunch of more people to use FPGAs without having to like start from scratch in USB 3. And unlike hardware, people can contribute back patches to the USB 3 core, and everybody's USB 3 core continues to get better. And like, we've seen this at Workshop, right? There's a couple of pending pull requests there to improve a couple of small bugs with the USB examples that we had. And like, this is from people who only got the hardware the last couple of days. They're already starting to help improve the system. You have basically the software style mentality applied to hardware development, and that's what really excites me, and probably what really scares hardware people. You know,
I mean, only in that I can't contribute. Well, not that I can't contribute, but I feel held back from contributing, you know.
It's been inaccessible for a long time, and I think that's part of why you feel that way. And I have too, really. Like you came more from the hardware side, and I came more from the software side into electronics. But for me, FPGAs have been kind of scary things for a long time, and they've been things that I've avoided. And so I kind of want to tie your last couple of questions together, like what makes FPGAs compelling for me as a designer, and also why is it important they're open source? Well, to a large extent, those are, you know, the same question to me, because a reason why I avoided FPGAs in the past was that I found, because they didn't have open source tool chains, that they were less accessible to me, and so I wasn't able to able to deploy solutions as easily, as flexibly. I wasn't able to gain the benefits of the open source community, and so in the past I've actually avoided using FPGAs on projects where I maybe that really could have benefited from, say, the flexibility of an FPGA. HackRF, for example, is kind of famous in the SDR community as being the SDR platform that doesn't have an FPGA.
And a lot of them do, right?
Yeah, most SDR platforms that are in that price range or above are FPGA based, and as Tim mentioned, FPGAs are really good at digital signal processing when you have high data rates that you need to do some number crunching on, which we have all the time in software-defined radio. That's a good application for FPGAs in theory, but I was trying to make the world's first open source hardware SDR platform, and I didn't want it to be dependent on closed source tools in order to write software or firmware for the device. I didn't want people to be unable to modify this thing because they had to pay for some proprietary tool chain that was unwieldy and inaccessible in other ways as well, because they're just big, as Ob's mentioned, and kind of have a big learning curve. They're kind of difficult to use. They take forever to download. There's licensing problems and high cost, and there are just so many different ways in which they've been inaccessible in the past. And now they're becoming much more accessible, and that's mostly due, I think, to having open source tool chain available. So I'm super excited about FPGAs in a variety of upcoming projects that I may not have considered in the past.
Well, how about upcoming projects too? Because so this stuff's now moving out of just the ICE40 realm, right? So we've got ECP5. Sean, what's the next one that is on the line?
It should be the Artix series, hopefully.
Yep, the Xilinx Series 7, the Artix 7, Kintex 7, those type of things.
So what is the gating factor on like getting more stuff in then? Is it just like Clifford and all them like reversing bit streams?
It's mostly contributors, and that's why I'm so actively interested in projects like Fomu and that, because it enables more people to get involved. And like the problem at the moment is the lack of developer resources in this field, and lots of it has very little to do with hardware. A lot of the work is taking one data format and converting it to another data format, and writing Python scripts and all this other...
It's like a bitwise janitorial duty.
Yeah, or like just describing what's in the hardware in a form that the tools can use, which requires reading a bunch of documentation and like copying the right details out of there and describe it in a way that the system can use it. And so like one of the points of the Fomu stuff is to make more people excited about FPGA so they contribute to these projects. And like
you need to hook them with a drug, right?
Yeah, the Fomu is like small, it's like candy. I can give it out like candy. The first one's free.
You're a pusher, man. You're a pusher.
And like once you're at a level where you're comfortable with FPGAs, all the stuff we're doing works on the bigger FPGAs, and it gives you a pathway to like go, oh, an ICE40 is too small for my use case. I want to move up to an Artix 7, and you can reuse a huge amount of your code. The same soft CPUs run on the Series 7 FPGA. They get faster, they have more memory, all these type of things. But that's mostly transparent to you. You just like, it's like moving from a low-powered embedded ARM to a higher-powered ARM. You don't have to rewrite all your code for your applications. You might have to rewrite a bit of driver code, but most of your code just gets faster and better. And this is the similar style of thing of what we're trying to do here, is like make reusable modules, make things that scale up. Like Lattice was always its own ecosystem, Xilinx was its own ecosystem, Altera was its own ecosystem. If you were in the Xilinx ecosystem, you only ever looked at Xilinx parts. You never looked at anybody else's parts. Whereas everything in the open source world is vendor neutral. So maybe you start with a project on a Lattice part and decide, actually, no, our Xilinx part is a better fit.
Yeah.
Maybe you start on a Xilinx part and decide, actually, I don't need as much power in the Xilinx part, and the cheaper ECP5 part is a better fit. And we actually have a tutorial that gets like Linux running on an FPGA, and the same tutorial works identically for Xilinx parts as it does for ECP5 parts. And so this means that doesn't matter where you start, you can move your project to the right platform for the product you're trying to deliver. And like
so before this is another question that Dave had for me that I could not answer. So Verilog is written as a generic thing across devices too, and so he was asking me like, well, can't you just port the code between the things? And I was like, I guess. mean, I thought I don't know. Like the tool chains are different, right? And the builds are different. But you're saying now, so then the power is actually in the programming and the compilation and everything else, or?
So, if you ever tried to write portable C code that works across multiple compilers, you'll find that every compiler is slightly different. This is significantly worse in the FPGA world, where they've been so separate for so long that like every FPGA toolchain has its own set of quirks and its own set of ways of doing things, and it becomes very hard to write portable code that works efficiently across multiple FPGA vendors. In theory, your Verilog should be, portable across different FPGAs, but like the way memory inference works in Quartus on our Tira parts is very different to the way memory inference works in Vivado for Xilex. And if you don't know this, you'll take your design from Xilex and try and run it through Quartus, and a design that takes, 10,000 gates in Xilex because it's using the memory will all of a sudden take 100,000 gates, and you're like, I'm going back to Xilex because I don't know how to fix this problem.
Got it. I see.
And in fact, like, this is such a known problem that if you're a big company and the big vendors are trying to court you, they will actually come and port your code from the other person's platform to their platform to try and sell you these parts.
Right.
And like, you shouldn't need to do that. And open tooling enables a lot of standardization. Like GCC has made a lot of the closed source compilers better. LLVM has made GCC better. Like the standards compliance of C and C++ compilers since like the 1990s has dramatically improved. And so, like, the interesting thing, I think, is, like, Sean is just about to start or is working on a project which has a Lattice FPGA and a Xilex FPGA.
Whoa.
And that is, like, a really strange thing to do previously, because, like, it means you're dealing with two totally different sets of tool chains and all this type of thing. And so maybe he can explain more about that project and what he's doing there.
Okay, so this is a project called Be Trusted, and this is a project that is primarily being done by Bunny. I don't know how much he wants me to mention.
Okay.
So there is a website, betrusted.io, and I think everything that I mention is on that.
I can pull it up here if you want me to have a cross-reference.
Okay.
Well, it's an interesting idea, though. I mean, maybe just, talking about having two on board is interesting by itself.
So the reason why we do that, the reason why there is this Lattice part and this Xilinx part, is that the Xilinx part idles, so if you just turn it on and let it sit, it takes about 300 milliamps, which is a lot of power. It's going to get a little bit warm, and that's completely unconfigured. Whereas I have this problem with Fomus, where if I put it in my USB battery pack, it turns off because it doesn't think anything's connected.
That's right.
So the ice parts, they call them ice because they're very cold.
Right.
They're very super low power, so they make great power regulators. So the ice part is going to wake up the Xilinx part when a message comes in that needs to be dealt with, and it will actually boot the Xilinx part.
So it's like a supervisor almost.
It's a supervisor. It's a controller.
Yeah.
It's takes care of keeping the system that's supposed to run on battery power for a very low power, so it can last for weeks instead of days.
That's cool. That's really cool. Yeah.
And because we're using this open source software, MeGen, LightX, all of these different tools to generate the FPGA code, we can reuse a lot of the software between the two platforms.
Yeah, that's great. Well, we're losing light, and surprisingly, I'm losing recording time. So we should probably start to wrap up here. What else should we know, at least about you, Sean, and maybe what you guys are working on as well? Let's go around the horn. Like, Sean, what's your day-to-day hardware struggles like? I mean, like, are you still getting the Fomu through production, or?
Yeah, so day-to-day struggles, we are trying to get Fomu through production. Turns out making PCBs is somewhat difficult, and we're just trying to get PCBs from the factory that are electrically sound, that pass the full electrical verification.
What are the specs on the board? Is that why they're?
Yeah, it's because this is a very small, thin, multi-layer board.
Yeah.
They're 0.6 millimeters thick. They're 4 layers with blind buried vias, edge plating, hard gold.
Because you're plugging them in and out.
Yeah, because we're plugging them in and out, so we want to make sure that they're reliable and that you can insert them. Because the way you reset a Fomu is by unplugging it and plugging it back in.
Right, you're not going to put a button on there.
Right.
And so that's the difference between the hacker board that I did, which has just ENG,
Right.
you know, it's technically only rated for like 10 insertions
Right.
or something like this.
Cross fingers.
But like, I'm giving it to you for free, so if it
Right.
breaks, I'll give you your money back.
Right.
But like, Sean's actually making a product that people can actually reliably use for long periods of time.
Yeah.
So currently the thorn in my side is getting the PCBs to be reliably manufactured
Yep.
and reproducible, so that we can actually do surface mount. We can run SMT and get the boards mailed to anyone who wants to buy one.
Yeah. Okay, that's great.
And I've been working on Great Vet things, getting Great Vet software and Neighbors, our add-on boards, into production, and so lots of
Similar
things,
struggles,
Great
huh?
Vet. Yeah, a little bit, but rather different aspects of the design and production are difficult for my projects, I think, than Sean's, but I can definitely relate. So my life is kind of all things Great Vet. In fact, I used Great Vet today to dump firmware off of a DEX device that a group of us was reverse engineering.
Nice.
So I've been having a lot of fun with the thing, in addition to trying to make more Great Vet things.
Yeah, and keep an eye out for Great Vet with more reconfigurable FETs in 2020.
Yeah, well, and one of the key neighbors that that is getting close to production now actually has an FPGA on it, and
nice.
we use it for its flexibility, so that you can do things like remap pins to different peripherals on the microcontroller, and it is sort of a very fancy level shifting solution. And having the FPGA on there gives us this kind of crazy amount of flexibility that we wouldn't be able to have any other way.
That's great. Tim, how about you?
Lots
of projects. We know.
Yeah.
We know. It's cool.
I think I'm concentrating on trying to get more people involved with the projects that I'm working on.
Actually, that would be a great lead-in. So how could people get aboard and get started? And
so my general policy is, if you send me some type of pull request, I will send you hardware. I've sent hardware pretty much to every continent except Antarctica. So people in Antarctica need to pick up their game.
Murdo Station? What's
McMurdo, yeah.
McMurdo, that's it, yeah.
If you go to the tomu.im website, we're working on trying to make it easier to find out things that you can help with. And I'm kind of a equal opportunity type person in, like, it doesn't have to be pull requests. If you're like helping do workshops, or you're helping with documentation or social media or any, like, if you're contributing to the community, I will send you hardware. I've sent Fomus. I send people bigger hardware. In fact, just this weekend, I've sent a whole bunch of people some bigger FPGA boards who want to work on some SymbiFlow related stuff.
Great.
I sent some other people some stuff to work on for USB 3. So, yeah, if you go to the SymbiFlow website, there's a link to the ideas page, which has a whole bunch of things we'd love people to work on. And, like, even if you're not involved in hardware, like, we're interested in people who can do web app development, because we want things like a really nice web IDE for doing FPGA development. We want a nice system for viewing the bit streams in FPGAs and like decoding them. There's a really great site, I think it's called like Godbolt, that like lets you put C code in and see how it maps.
Mad Godbolts, yes.
We would love to see something similar to that for FPGAs, and most of that isn't hardware stuff. It's about, you know, building,
making it accessible, making it
and
increasing community. Yeah,
that's all web development. So like, I love for more web developers to come along, and like, it doesn't matter if you're doing that. I'll send you hardware anyway. Like, you know.
Well, it's good though. I think if people are excited,
out you'll become a hardware developer.
Yeah, everyone's just a hardware developer in waiting. Yeah, watch out, folks.
It happened to me.
Yeah, right. Well, guys, thanks for joining here, and I'm glad to hang out at camp. This has been a lot of fun.
Yeah.
Thanks for having us.